Today I'm going over a newly reported principles of flight question, which, other than being impossible, is quite straightforward. Now, that might sound strange. I suspect it's poorly reported feedback because the question as presented from the source I found it is not possible. It doesn't have the right information you need. But a similar question can be answered. There's really only one question you can answer from the information provided. So we've got to assume that that is the actual question. Likely that the ECQB, the Central Question Bank, the EASA Central Question Bank, will give this correctly, not as I've shown here. Yeah, when you assume that, when you assume we're answering a slightly different question to the one actually presented, it's not a particularly difficult question. What it is two familiar questions, one after the other. So we are going to cover fairly familiar territory in answering this question. So the question is, using the following information and a TAS thrust required and available, so thrust required, thrust available graph, what is the maximum vertical speed of a 3-engine turbojet aircraft with 1 engine in operative? So we've got operating on two-thirds thrust. Sorry about that. What is the maximum vertical speed of the aircraft? So vertical speed, that would just be rate of climb. And so the answer, we want the answer in feet per minute. And the information given here is that the aircraft mass is 75,000 kilos, gives acceleration due to gravity of 10 meters per second squared. As I hope you're aware, that means that every kilo of mass weighs 10 newtons. Then gives an approximation to the conversion between knots and feet per minute of 1 knot equals 100 feet per minute. That's a good approximation, it's a very close approximation, in fact. The actual figure is 101 1/3, 101.3 feet per minute. But this is a very commonly used approximation if you haven't come across it before. Then it gives you a formula that you actually are supposed to know, which is that sine of the angle of climb, sine gamma, is thrust minus drag over weight. What it doesn't say is that we're going to be using that as an approximation to the climb gradient. Okay, so that's going to be approximately equal to the gradient of climb. The reason that approximation works is that the gradient of climb is tan of gamma, tan of the angle of climb, and for small angles, sine and tan are very, very similar, and all our climb angles and descent angles are, for normal operations, are actually quite small enough that that approximation is pretty good. Typically within significantly less than 1.5%. And certainly in this question, it's around less than 0.5% error, I believe. So it's always suitable to use for exam questions. Right, so what's the graph we've got then? Okay, so in order to find a rate of climb, what we're going to need is we're going to need a gradient of climb, then apply that gradient, then use that gradient and the speed of the aircraft, the horizontal speed, or rather the airspeed of the aircraft, to then work out the rate of climb. And so we need a few pieces of information. We need the aircraft weight. Well, we've got enough information already to work out the aircraft weight. We need thrust and drag, so we're hoping for that from the curve. It's a thrust required and thrust available curve. And we need the aircraft speed. And since the question asks for maximum vertical speed, it's asking for, specifying here what's the maximum vertical speed, then we want all of those at VY 1 engine in operative. Yeah, so that should be the position, that should be the information given to us. Now, here's our problem, because when we look at the graph given is something like this, where it's a thrust required and thrust available against TAS graph. It's not quite standard, of course. Mostly if we use thrust curves, thrust required and thrust available curves, then we'll do it against CAS. Of course, thrust required is more familiar to us as drag, because when they say thrust required, what they mean is thrust required straight and level. And of course, the only thing to overcome straight and level with thrust straight and level is the drag. So this is just a familiar drag curve, usually put against CAS, but as long as we've got a constant density altitude, that doesn't matter. That makes no difference. The problem here is the information they've given us, because the information they've given us is at the bottom of the drag curve, at the lowest point of the drag curve. And I hope you're aware that this is actually Vx, and Vy, whether one engine operative or not, is going to be somewhere to the right of here. So that's really why I said at the beginning that this question is impossible. This question as presented is impossible. They haven't given us the right information. They've given us information about Vx and not about Vy. So if we go back to the question, let's correct the question. What they want is the maximum the vertical speed at the best climb gradient or angle. Now, probably gradient, because of course all the regulations tend to talk about gradient when we're talking about performance regulations. But here we go. So we want to know the vertical speed at the best climb gradient, because that's all we can work out from the information presented. That I don't know how they're going to express it exactly in the exam. This exact wording isn't actually even what's reported. This is the question. This is not exact wording as reported, but in some way they're going to ask you the vertical speed of the aircraft, or the rate of climb of the aircraft at your best climb gradient, because that's what we can work out. We can't actually work out anything else that's meaningful from the information presented. Okay, so in order to work that out, we need, as I said before, we need three things from the graph. Well, I said before, in fact, I said we need thrust and drag, and we also need a speed, because we're going to need to apply the gradient of climb to an airspeed in order to work out the rate of climb. So we need thrust and drag and speed from the graphs. Thrust is very easy. Okay, so if we look at the graph, the thrust available, all engines operating, is given us 240 kilonewtons. So of course, if we've got one engine inoperative, we're going to get the thrust, that's probably a bit high, we're going to get thrust somewhere down here of 160 kilonewtons, which is 2/3 of the thrust with all engines operating. So we can go into the question page here and add that in. So we can say thrust equals 160 kilonewtons. So next thing we want is drag, and again, the only drag they've given us is at Vx, so it's given us straight 110 kilonewtons of drag at Vx. And we want to know what Vx is as well, although it's not really Vx because obviously it's a TAS, but it's Vx expressed as a TAS in the given density altitude. Okay, so Vx, so thrust is 110, drag, thrust available, thrust required. It's given as in the graph. In the graph, it's given as thrust required is 110 kilonewtons. And the TAS is 190 knots. And so if we convert the mass into a weight, so we use these two figures to find that the weight equals 750 kilonewtons, so 750,000 newtons. We'll just express that as kilonewtons, then everything's in the same units. Or all the forces are in the same units. We can now work out the approximate gradient of climb. So let's go on to that. So gradient equals thrust minus drag over weight, which in kilonewtons is 160 minus 110. Notice it doesn't matter what units I use as long as I'm using consistent units. So I'm using kilonewtons as the unit here. I don't need to go to newtons and stab extra zeros into my calculator. So divided by 750 kilonewtons of weight. So I got 160 minus 110, that's 50, divided by 750 equals, give me 0.067. Now, usually, of course, we'd multiply that up by 100 to turn it into a percentage if we wanted to just know the gradient. So this is actually a 6.7% climb gradient, which sounds very reasonable for one engine and operative. But that's not what we want to do today. So today we want to convert our horizontal change into a vertical change. Okay. And for that, first off, we need to convert TAS into feet per minute. Okay, actually the order doesn't matter, but what we'll do is we'll convert TAS into feet per minute, and we're given the conversion here. So I'll take 190 and just multiply it by 100, and that gives us 19,000 feet per minute as my TAS in feet per minute. And all we then need to do is multiply that by the gradient to find the rate of climb. That's the answer to the question. Actually, this is one of the few times when I tend to use gradients a lot. A gradient, remember, is the ratio of the vertical change to the horizontal change. Yeah. So if I have a vertical change of y, a horizontal change of x, gradient equals y over x, which, by the way, that's where the tan comes from. Oh, my gammas aren't very good, sorry. Okay, so tan of gamma, our climb angle there. So obviously this is a climb. Tan of gamma is opposite over adjacent. Tan is opposite over adjacent, which is y over x, which of course is the same as our gradient. Okay, so if gradient is y over x, if I want to find y, which is my vertical change in feet per minute, okay, so my vertical change in a minute in feet, if we've got everything in feet per minute, which is nice, okay, then I rearrange this equation and I can say that y equals the gradient multiplied by x. Now, I hope that this is fairly standard stuff. I don't want to go over into too much detail, but if you're unsure of that, let me get in touch with me. Some of this is actually covered in maybe some of my other videos. Yeah, but that's how we convert a horizontal change via a gradient into a vertical change. So all we need to do now for the final answer is 19,000 feet per minute multiplied by 0.067. So multiplied by 19,000, giving me 1,267 feet per minute. That is the answer to the question. And that's the answer that the Commercial Question Bank got as well. So obviously they've done the same. They've made the same assumptions. Again, this is not the maximum vertical speed the aircraft can achieve. If the aircraft was flying at VY, so a slightly higher airspeed, then it would achieve a higher rate of climb. This is actually at best gradient of climb speed, because remember, for a jet, for a jet, Vx is at minimum drag speed, and this is showing the details of minimum drag speed. So the question isn't quite correct, but this is the only answer you can calculate, and this is what others have agreed is the correct answer. So if anyone comes across this question in the real exam, then could you please get in touch with me either through the comments below or on the email at the beginning of the video, and yeah, we'll try and see if the question is any better or if it really is like this in the Central Question Bank. And thank you very much for watching the video.